My name is Brittney Johnson. This summer I had the opportunity to study the impacts of extreme precipitation on water in the subsurface. My project mentors were Shemin Guh and Claudia Corona. The motivation behind my work stemmed from the increasing demand of groundwater resources and the lack of understanding and accuracy in predicting current and future recharge of groundwater systems. The objective of my work is to better understand how varying precipitation affects infiltration and soil water storage in the subsurface. My study area is Gordon Gulch, a 3.6 square kilometer drainage basin located in Netherland, Colorado, ranging in elevation from 2,446 meters to 2,737 meters, placing it in the montane climatic zone. In the lower area, you can see Gordon Gulch, where I conducted my study. There are 3 different areas where I collected soil samples, indicated by an orange square, and then the blue dots indicate the areas where I conducted double ring infiltrometer tests. Gordon Gulch is located in the larger Boulder Creek watershed, highlighted by this square, and within Colorado, it is right there. To best understand the history of precipitation and the response to soil moisture in the area, I decided it would be best to look at a 2-year period, which included an extreme rain event. To do this, I looked in between the time of October 2012 and September 2014, and I graphed precipitation, which is indicated by the dark blue line, and soil moisture, which are these cluster of colorful lines. And from that, I was able to look at the response of soil moisture and over fluctuating periods of precipitation. The smaller graph shows the 2013 flood event and the response of soil moisture to that fluctuation in precipitation. 3 methods that I used to collect data, or 2 methods that I used to collect data were in the field and in the lab, and then I summarized those results to simulate a computer model of varying precipitation over time to show the difference in soil moisture. In the field, I conducted 3 double ring infiltrometer tests. To do that, I created a leveled surface. I removed plants and roots from the surface. I filled the outer ring with water to reduce the lateral flow of water through the soil, and I filled the inner ring. I then recorded the water level drop over time, and I repeated this process for a total of an hour. In the field, or in the lab, I did permeameter testing to calculate the hydraulic parameters of my soil samples. To do this, I measured discharge, the length of the soil sample, the area of the sample container, the pressure of the permeameter, which was set by a PSI gauge on the panel, and then I measured the test duration. I then took all of this measurements and I used Darcy's equation to determine the hydraulic conductivity. Within HYDRUS 1D, I used 3 different soil profiles. I modeled 3 different cases, 2 heterogeneous and 1 homogeneous, and each column was 1,700 centimeters in depth, and the different colors correspond to the different hydraulic conductivity values. The results of my double ring infiltrometer test gave me infiltration rate, showing the infiltration capacity of the soils that I had collected. From these results, you can see that the hilltop has significantly lower infiltration capacity than the slope. And infiltration capacity is just the ability of water to seep through the soil. I didn't say that. From the permeameter, I was able to collect 3 hydraulic conductivity values. For the hilltop, that K value was 20.6 centimeters per day. For the valley, that value was 42.2 centimeters per day. And at the slope, the hydraulic conductivity value was 716 centimeters per day. So, the purpose of modeling subsurface flow the purpose of modeling subsurface flow using HYDRUS 1D was to identify changes in the soil water storage for 3 cases over a 150-day period. On the far right, we can see this diagram of the unsaturated zone and the saturated zone in relation to the water table. For each of the 3 soils that I collected in the field, they were all located within the unsaturated zone. This figure shows the relative depth of soil layers that I used to create the 3 soil columns within HYDRUS 1D, those different colors. And so onto the modeling part. My initial conditions for HYDRUS were 150 days of precipitation directed to the top of my soil column of 1,700 centimeters in depth, and that ranged from initial pressure head from negative 100 centimeters at the top to 0 centimeters where the pressure is 0 centimeters at the water table. Of the many modeled outputs that I received, one was for the homogeneous soil of sandy clay loam with a hydraulic conductivity value of 31.4 centimeters per day. From this graph on the right, you can see the difference in water content that varies over depth through time. These 3 lines indicate during the event and after the event, days after the event. The blue line shows that water content increases as it goes farther down in depth before that wetting front crosses. And then at that point, that's when the precipitation amounts in that area have stopped raining down. So they've lessened, and thus the water content is decreasing. And then at 6 weeks, the water content has now become like a steady rate of like decreasing through depth. And then at 11 weeks, the soil moisture recovers to background levels. And background levels are generally around like this curve right here, which is more of a lower depth where water or precipitation is less likely to impact soil moisture behavior. The objective of my research was to understand how varying precipitation affects soil water storage. And so to do that, I plotted the homogeneous soil versus the hilltop and the slopes layers. And that showed that soil water storage and field data have an agreed general pattern, which is seen by the infiltration graph, where the hilltop has a significantly lower infiltration capacity than at the slope. Here we can also see that soil water storage in homogeneous soils differs from multi-layered soils. And so there, at the top, we see that homogeneous soil can store about double the amount of water than the hilltop and at the slope. 3 conclusions that I have from this are that soil water storage fluctuates with change in precipitation. Infiltration through the subsurface is affected by soil heterogeneity as well as hydraulic conductivity, and changes in soil heterogeneity affect the amount of water that can be stored within the profile. I would like to acknowledge NSF for funding this opportunity. As well, I would like to thank Andrea Ellis, Lon Abbott, Becky Simon, Megan Brown, Emily Fairfax, and Rachel Havernack for all the work that they've done for me. Thank you.
Great job, Brittney. We have questions. Oh, there's Lon.
Thanks, Brittney. So I was struck by your field photo of when you did your double ring infiltrometers, and it looked like there were a few centimeters of material at the top that was removed. And because that's going to be like the A horizon, I'm wondering if you're worried that your experimental setup is actually changing the permeability characteristics of your soil compared to what if they were undisturbed. And the hill slopes were so much higher, I'm thinking that to get the level surface, you're going to need to take down more in the on the hill slope. So I'm wondering if that experimental method, do you think, has any kind of bearing on your results?
With my results, I was only trying to simulate subsurface flow, and so that required me to remove the layer of roots in soil and like the roots, yeah. So then by doing so, I was altering the surface a little bit. However, it wasn't going to affect what I was trying to measure.
Other questions?
So when you talk about the hilltop versus the slope, what difference in gradient are you?
The hilltop at Gordon Gulch is kind of like a plateau in a way, where like it's sitting on top of a hill. And then the slope is more of an angular, like slope downhill, in like a southward direction. And so they're just varying in the amount of soil that I had to take off, as well as just the lateral flow that would have affected my test results.
Did you happen to measure the gradient of the slopes?
I did not.
Okay.
Any other questions for Brittney? All right. Thank you very much, Brittney.
Oh.